Sip Hub. Welcome to another episode of our series on mathematical language and symbols. In this presentation, we will be talking about one of the most important concepts in mathematics. It's called sets. But before we continue, do not forget to like this video, hit the subscription and notification bell to stay updated of future videos. By definition, set is a well-defined group or collection of distinct objects. The objects are called elements or members. These elements are listed inside a pair of braces. We emphasize that it should be inside a pair of braces, not parentheses or brackets. It should be a pair of braces. And we name them using capital letters. That's the convention. When we put names to our sets, we normally use capital letters. We realize that when we talk about sets, we are not necessarily talking about numbers only, but any objects that we can think of. We can have a set containing people, or a set containing places, or a set containing countries, etc. In our definition also, I would like to emphasize the term well-defined, because not all collection of objects is to be considered a set. It has to be well-defined. And we say that the group or collection of those objects are well-defined if, for a particular element that we can think of, we can decide whether that particular object is included in that set or is not. I believe we can understand this more if we present some examples. Let's say A is the set of all students currently enrolled at BSU. Clearly, we are collecting students who are currently enrolled at Benguet State University. But the question is this a well-defined group of objects? The answer is yes, it is well-defined, because for a particular student that we can identify, we can decide if that student is included in set A or is not included in set A. For instance, if we identify a student from St. Louis University, then we say that that student is not an element of set A. Another example, B. The name of the set is B, and this is the set containing all beautiful people. Do you think this is a well-defined group of objects? Beautiful people. The answer is no. B is not a well-defined set, because identifying whether a person is beautiful or not is subjective. For instance, your mother might consider you beautiful, but your neighbor would say otherwise. This is an example of a group of objects that is not well-defined. So this is not considered a set. C is the set of all even numbers. Given a number, can we identify whether it is even or not? The answer to that is yes. Therefore, this is a well-defined group of objects. So C is a set. D is the set of all numbers close to 10. What is a number that is close to 10? Is 9 close to 10? Some of you might say yes, some of you might say no, because to them, a number that is close to 10 is 9.9 and not just 9. Or even for other people, 50 is a number close to 10, because in their mind, 1 million is a number that is not close to 10. So you see, this group of numbers is not well defined. This is not a set. Let's provide more examples. Let me name this set A. The name of the set is A. As was mentioned a while back, we need to enclose it with a pair of brackets. The elements are, how many elements do we have? 1, 2, 3, 4, 5, 6, 7. Sunday, Monday, Tuesday, Wednesday. So it's the days in a week. Another example of a set, B. It's named B. These are the letters in our English alphabet. Specifically, these are the small letters. This method of writing a set is called the roster method. In this particular method, we are writing exactly what the elements of that particular set are. For instance, in this particular set, we can exactly pinpoint what are the different elements that the set contains. There are 7 elements. Also, for this set, it's written using the roster method because we are simply listing exactly what are included in the set. Another method of writing a set is called the set builder method. In this method, we are not directly writing the elements, but we are simply describing them. For instance, if we write the same set here, but in set builder method, we may write A is the set of all X such that this symbol here is read as such that X is a day in a week. You see, these sets are the same but written in different methods. In this method, we cannot directly see what are the elements, but it is just describing the elements. It's just a day in a week. How do we write set B using the set builder method? Instead of directly writing them, we can describe them as the set of all X such that X is a lowercase letter of the English alphabet. There are advantages and disadvantages of the two methods. Normally, when it is more important to describe rather than directly listing the elements, then we use the set builder method. Also, we normally use the set builder method when the set contains a lot of elements. You imagine a set containing 1,000 elements, and it would be tiresome to be listing all the elements. It is better to use the set builder method. Also, the set builder method is more appropriate to use for infinite sets. We will tackle the idea of infinite sets in a moment. The roster method, on the other hand, is more appropriate for finite sets containing fewer elements. As mentioned a while back, sets does not necessarily contain numbers. But in this course, of course, we are more concerned with sets whose elements are numbers. And throughout the course, these are normally the sets of numbers that we will be dealing with. Let's start with the set of natural numbers, otherwise called counting numbers or positive integers. Note the symbols that we are using here. If we call it counting numbers, the symbol is C. If we call it natural numbers, we call it N. The symbol is N. And if we call it positive integers, we use this symbol. This is the Greek letter zeta. And then we put a subscript that is positive to denote positive integers. And this is a set of numbers starting from 1, 2, 3, and so on, so forth. This is our ellipsis indicating that the set is progressing indefinitely. Very simple. If you are asked what are natural numbers, you just count the number of fingers you have so that you would start with 1. So natural numbers starts with 1. Because when we add the element 0 to the set of natural numbers, then we have another term for that. We call them whole numbers, the set of whole numbers. Symbol is capital letter W. We see here that this is our natural numbers with the inclusion of the element 0. In other words, the set of natural numbers and the set of whole numbers are almost the same in terms of the elements. The only difference is that 0 is included in the set of whole numbers. Negative integers is the set containing the negative counterparts of the positive integers. So it's just the same. It's 1, 2, 3, 4, and so on. It's just that they are negative. When we combine all the elements of negative integers in whole numbers, another set is formed. They are called integers in general. So if we look at the elements, it's the combined elements of the set of whole numbers and the negative integers. So in both ends, they are progressing indefinitely. In this side are the whole numbers, and then these sides are the negative integers. Another set of numbers, we call them fractions. I believe we are all familiar with our fractions. If we combine the elements of integers in fractions, we have another term for that. The set that is formed is called the set of rational numbers. The symbol is Q. If a number is not rational, then it should be irrational. The symbol is Q prime. Quickly, what are examples of irrational numbers? We have your pi, you have your Euler's constant E, we have square root of 3 or square root of 2. These numbers when we put them in decimal form, they are non-terminating, meaning it doesn't end, and non-repeating. Non-repeating means there is no particular pattern that we can observe on those decimal values. If we put them in decimal form, they could be terminating, so it ends, that's a rational number. And if it's non-terminating, it doesn't end, but repeating, there is a pattern formed, then that is considered a rational number. If we combine all the elements of the set of rational numbers and the set of irrational numbers, the set formed is called the set of real numbers. We can see the symbol that we use for this particular set. These are our sets of numbers. Let us differentiate null set from a unit set. A null set is simply a set with no element. Very simple, but I would like to emphasize on the symbols that we use. We have two options. If we mean a null set, a set containing no element, we use the Greek letter phi. In chapter 1, we use this symbol to denote the golden ratio, the value for it. But under sets, phi means a null set. An alternative symbol for phi is a pair of braces with no element on it. We cannot write this way. This is not a null set because obviously the set contains something. It contains the null set. A unit set, from the term unit, is a set containing only one element. So here are some examples. The set containing 1, the set containing A, and the set containing phi. Actually, this is an example of a unit set but not a null set or empty set. Difference between finite and infinite set. Finite sets are sets whose number of elements is a whole number. This means that if we count the number of elements of a finite set, at some point we stop counting because there's nothing to count anymore. That is a finite set. This number of elements is called the cardinality of the set, denoted by n of a. This is your set, and if you attach the symbol, the small letter n to it, you are actually asking how many elements does that set have. Let's have an example. Set A is the set containing 4 elements, 1, 2, 3, and 4. N of A means the number of elements contained in set A, and that is 4. So the answer for this one is a number. Infinite sets, on the other hand, are those that are not finite. This is a bit complex, the definition here, but what this means really is a set is considered an infinite if the elements of that particular set can be put into one-to-one correspondence with the set of natural numbers. This is actually an example. The set of integers is an example of an infinite set because when we are going to pair its elements, the elements are 0, 1, negative 1, 2, negative 2, and so on. If we pair it to the set of natural numbers or counting numbers, there will be a one-to-one correspondence between the two sets. One-to-one correspondence means that for both sets, each element has only one partner from the other set. For instance, all the elements here is only paired to one natural number. And also, from each of the elements of the sets below, it is paired to only one element of the set of integers. That is what we mean by one-to-one correspondence. If a set violates this, then it is not considered an infinite set based on this definition. Another concept, equal versus equivalent sets. We say that two sets are equal if they have exactly the same elements, regardless of order. They are equivalent if they have the same cardinality. This means that equivalence is only pertaining to the number of elements the two sets have, whereas equality of sets is pertaining to the elements themselves. I have a question here. If two sets are equivalent, is it necessary, does it follow that they are also equal? The answer is no. Because as I have said, equivalence only is concerned on the number of cardinality. Two sets might have the same number of cardinality, but the elements of one set is different from the elements of the other set. For example, the first set contains 4 numbers. The second set contains 4 letters. Both of the two sets contains 4 elements, but the elements are different between the sets. The elements of the first are numbers and the elements of the second are letters. How about this one? If the two sets are equal, does it follow that they are equivalent? The answer is yes. That must be the case. Okay, we end with something to work on. Here are 5 pairs of sets. I would like you to identify if they are equal, equivalent, or neither. Of course, if we say equal, it automatically means it's equal and equivalent. If it's equivalent, it's only equivalent but not equal. If it's neither, then we simply say neither. I would like you to think about this and then comment your answers below. You may pause this video if you need more time, but please put your answers first before you proceed watching this video. Let us have the answers. Number 1, obviously they can never be equal because they have different objects or elements. One has letters and then the other has elements that are numbers. But are they equivalent? Let us simply count the number of elements. We mean the cardinality for each set. 1, 2, 3, 4, 5. There are 5 elements. The cardinality of this set is 5. 2, 4, 5. Also, the cardinality of this set is 5. They are not equal, but they are equivalent. Number 2, both sets contains numbers. But if we count the number of elements, we only have 4 for the second element. So they can never be equal as well. They are not also equivalent. So our answer is neither. Number 3, the first set is written using the set builder method. So it's a bit tricky if we are presented a set written in this way because this is, again, just a description of the set and we cannot directly see what the elements are. For the second set, it's written in roster method, so it's easier to deal with this one. 2, 4, 5, these are Greek letters. It contains 5 elements. Let us write this one, the first set, in roster method so that it is easier to decide. This set is the same as the set containing 0, 1, 2, 3, 4, 5 because this is the set of all x such that x is an element of what is this set? This is the set of whole numbers. So x is a whole number that is less than or equal to 5. What are those numbers? We started with 0 because 0 is a whole number and it should be less than or equal to 5. So 5 is still included. How many elements do we have? 1, 2, 3, 4, 5, 6. We have 6 elements. In the second set, we have 5 elements. So they can never be equivalent. So the answer is still neither. Number 4, we have a finite set for the first set. They are multiples of 5 starting from 5 and ending with 80. How many elements do we have here? The second set is again written in set builder method. Before we decide, let us first count the number of elements in the first set. There are 16 elements in this particular set. If you do not believe me, you can pause the video and count it yourself. This set is equivalent to a set containing the numbers 1 to 16. Why? Because this is the set containing all x such that x is an element of the set of natural numbers, but x has to be less than 17. It's less than 17, so 17 is not included. That's the reason why we ended with 16. There are 16 elements for the first set. There are also 16 elements in the second set. Obviously, they are different, so they can never be equal. But they are equivalent because both of them have 16 elements. I mean the sets. Number 5 is obviously equal. There are 4 elements, and if we investigate each element for both sets, we see that they are exactly the same. Well, of course, the second set has different order, but it doesn't matter. 1, 2, 3, 4 are the elements of the first set. Also, 1, 2, 3, 4 are the elements of the second set. That's it for our introduction for sets. I will see you in the next video for the continuation.